Multiple startups are exploring ways to reduce the methane emissions from ruminant livestock, so think belching cows. But which approach makes the most sense? I'm here in Singapore at the Asia Pacific Agri-Food Innovation Summit with Dr. Steve Meller from CH4 Global to get his take.
Cows burping is the single largest source of methane globally, larger than all of the methane emissions from the oil and gas sector. So it's a major problem, but it's also a major opportunity if you happen to have a platform that could do so in an effective, cost-effective, and safe way. That's what we do.
So your approach is red seaweed. What is in red seaweed that can reduce methane production in cows, and how effective is this approach versus other approaches in the industry?
The actives, the bioactives in Asparagopsis, and there are more than 100. Don't let anyone tell you there's one, because that appears to be the rhetoric, but there are clearly about 100. That one is the highest concentration, but it's not the only. They all interfere with that enzymatic assembly of methane in a very well-known biochemical approach and way. Nothing magic about it, that's just what happens. So if you have the right amount of the material in the right concentration, because your process has defined it, you can now have a very effective solution, much more so than anything else on the planet today.
So what kind of percentage reductions are you talking about in methane
So the
production?
published studies that have been done, primarily in beef feedlots, less so in dairy, but there have certainly been some, they all support effectively 80 to 95% with good quality material. You'll see reports 38% or 30% or 40%. That's generally coming down to the fact that it's poor quality material. The bioactives in there are either not stable or they're not the right concentration when they were used in here. So good quality material, critical to have. It's in the 80 and probably closer to 95% reductions.
So everyone says, okay, this stuff works, but the challenge is growing it at scale. You're growing it in land-based tanks. Why not grow it in the ocean or in another process?
So we have grown it in the ocean, as have others. And what we've quickly become to understood is the variability of ocean temperatures, the other environmental factors that go on, availability of nutrients. And this plant, it's an aquatic plant, like most plants, have a seasonality to them. And so that seasonality means they flower, if we want to use that same analogy, for a portion of the year, perhaps 3, 4, or 5 months. And we understand the triggers by what does and doesn't cause those changes, but it means you have a short season. You have variable material. You can never actually understand the quality of what that product is. And now you have to go through a manufacturing process of very high variability in terms of quality to bring it down to a very small variability in terms of a quality assured product release characteristic. Just not feasible to do in any commercial basis. We've run all of the numbers every which way from sideways. And when you move on to land, most people, including ourselves today, grow it in what we'll loosely call tanks. Those tanks have various shapes and sizes to them and volumes. And again, we know, because we've used all of those shapes and sizes and volumes, again, that it's just simply not commercially feasible to get to profitability. So we think about the systems, what are we doing differently? It's really both in the growing and the processing. Both of these are the significant drivers to cost. Cost in terms of the hardware, cost in terms of the land, cost in terms of the energetics required to drive the systems. In the growing systems, we've tried to adapt what we know works well in tanks, the nutrient levels, the mixes, and light being a part of those nutrients. But we're limited on the size because of light penetration problems that you have when biological systems grow. So we've chosen to build systems that we build into the earth, partly to use as insulation factors, but partly to lower costs significantly, and created certain conformational shapes and sizes and depths and a variety of other characteristics that are all part of the patent applications that really describe how do you maximize the penetration of all of the nutrients, dissolved CO2 in the water, the nitrogen, the phosphorus, and importantly the light. And how do you do that in a cost-effective way where you can bring COGS down 7 to 10-fold? That was the objective, which we're able to meet. We've got prototypes of those built. We know it achieves high levels of growth with those types of cost reductions. On the processing side today, people have tended to have used freeze drying. Typically it's used in the fruit and veggie industry widely. It's incredibly energetically expensive, as is the equipment, with very long lead times. Not a commercially feasible way to do this at scale. Others have looked to extracting out certain of the bioactives using an oil base. We think that takes you down a regulatory path that why if you don't have to? And there's really little data published at the moment that tells you about what comes across, its profile, its stability. And we also know that there's a reduction in loss. So these 30 to 50% losses in processing, frankly, are unacceptable from a manufacturing standpoint and background. So we've driven and filed some key IP around 2 different ways to deal with that. Both of them used widely commercially for decades and decades, lots of commercial validation. It's not a new whiz-bang technology that we can patent. We've patented the approaches for the applications we're using, and collectively the 2 of those have brought COGS down significantly in the 7 to 10-fold, making it affordable for farmers and also making it profitable for us.
So you've recently raised a Series B round to help scale up your operation. Tell me about your manufacturing setup.
So the Series B for us is still ongoing. We announced an early close of 29 million. We've continued to raise more money, and we're very close to our 45 million goal now in a time and environment where it's incredibly hard to raise money. So we're very proud and happy to bring in some of those commercial partners who are also very well embedded into the ecosystems for us. So there will be other follow-on advantages that'll come as we scale. What that's enabled us to do, though, is to create the CapEx to build what we call the world's first commercial scale facility. We call it an eco-park. And eco-park 1, which is the first one in here, already has 100% of the output pre-assigned to 3 commercial partners. All have been publicly announced. About 10,000 cattle's worth for each of 3. The facility, when it's fully up and running, should generate, upwards close to $20 million in revenue. But its really important goal is to validate the financial metrics. We'll know CapEx, we know OpEx, we know what the pre-sold prices are. We'll be able to define its profitability in terms of its gross margins. We already know today it's going to be net positive in terms of gross margins. And we've been in discussions with very large-scale infrastructure lenders for building larger scale facilities for commercial partners, like Lotte, which we announced here about 3 weeks ago, which was the supply to the entire country of South Korea, 4.1 million cattle. Let's just say that's not an inexpensive facility to build for 4.1 million capital. So we're trying to line up the ability to be profitable with agreements in place that demonstrate demand at very large scale, with scaling infrastructure partners to write large checks to meet that demand based on profitability. That's work that we have going on at the moment.
So finally, what are the incentives for farmers to use your feed supplements?
What we know from the work we've been doing is we'll use Australian beef as the first market we're going into as the context. Somewhere between a 2 and a 3% premium is all that's required to 100% cover the total costs of the product. More than that, farmer puts money in their pocket, so they're incentivized. But they have a second lever, which is feed efficiency, or as long as the methane is no longer being burped out, that carbon and hydrogen stays within the rumen and can be redirected back into increased efficiency, or translated better for the farmer, a likely reduction in feed intake to get the same level of output. That's in the low single digits as well, to 100% cover the cost. And the third lever is the value of carbon. And the carbon reduced from a cow, when you're at 90%, is somewhere in the range of $130 to $140 a ton. World's not there yet, but it may get there. They're all independent variables. So if the farm had all 3 of those, you can do the combinatorial analysis, and if they get more than that, it's money in their pocket. So it's very important to bring costs down to make it affordable for farmers without the need for incentives, because incentives are a false hope and will go away. The fourth larger one, though, that's really important, that really nobody talks about, is the value of taxes, or the impact of taxes in this equation. We know that New Zealand and California have both implemented taxes. We know the Netherlands has ongoing protests about mandatorily acquisition of up to 25% of the total farms that the Netherlands government has announced, where they set aside 21 billion euros for that in 2021. We know that Ireland has recently been in the news, leaked news stories about culling 200,000 cows. So this is real and it's happening now. We know the EU implemented earlier this year carbon taxes on steel and cement. I believe, from some information we have, that will extend to agricultural products into next year. So these are going to impact farmers. They may not today, but the impact of those will be much larger. You may have markets closed off from you.